Okay, now let's go for the GaussDB architecture chapter. So first of all, GaussDB is next generation enterprise level distributed relational database services. It supports SQL 2003 syntax, which means it supports most of your application SQL statements. And it provides the high throughput and a strong, consistent transaction processing capability, which is most suitable for core systems used widely in industry, such as financial, telecom, and governments. We provide both primary standby and distributed deployment mode. For the distributed GaussDB, it eliminates the storage and performance bottleneck of a single database server. It can provide a highest throughput, which will meet the peak traffic requirement of your core systems. So what is the system architectures? So first of all, let's go through the primary standby instance. In this diagram, it shows the core components. We have the OM, the operation manager, provides the operation and management dashboard for underneath your GaussDB cluster. We provide the cluster manager, which will handle all the cluster communications and control. The most important part is here. The DM, data nodes. The data nodes is where store all your data and execute the SQL agents and the storage agents. Each of the data nodes will connect to our storages. So you will see that this is a shared native storage architectures. Also, we have etcd, which provide the data consistency. A little bit more complicated. We're talking about the distributed architectures. So you will see besides those components which were already introduced, there are two additional components. The first component, we're talking about the GTM, Global Transaction Manager. This Global Transaction Manager will handle all the concurrent data access and the data consistency between the multiple concurrent processes. Also, we have the CM, coordinate nodes. This one will become the interface from the client side and the internal data nodes. There are altogether 4 different table distributed modes in the GaussDB distributed additions. First of all, we're talking about the distribution tables. In this mode, the data will be copied to all the data nodes. While for the hash, list, and region, based on the distribute key, each of the data row will only be distributed into one data node. So you will see the key difference. For the replication tables, each of the data nodes will have a full set of the replication tables. Those kind of tables is mainly used for the global reference tables for easy of the join statements. While for your distributed data, based on your distribution key, it will be equally distributed to each of the data nodes, which means each set of the data is only stored in one of the data nodes. So the data in different data nodes will process concurrently, to speed up the total database performance. How to define the table distribute mode? So you will see the example here. It's have a statement called distribute by something. You will see, this table is distributed by the replication, which means this table, the content will copy to all the data nodes. And for this sales fact, it's distributed by distributing key, region ID, department ID, product ID, and it distributed by the hash algorithms. So for the sales facts tables, each of the rows is only located to one of the data nodes. So let's go to a little bit details. Why is the data nodes? So you will see that, okay, the data nodes, first of all, will receive the SQL statements from the client side. After it receive, okay, it will do all the syntax check to verify it's a valid statements, and it will optimize the execution plan. Once the execution plan is finalized and optimized, okay, it will be executed. It will check all the data dictionary cache for all the tables, those kind of informations, and it will retrieve all the data from the data buffer. After the transaction is finished, okay, it will write the redo log to the redo log buffers. There is a certain of the background process running on the data nodes to handle the interface between the memory and the disk. For example, if the SQL plan try to get some data which is not in the data buffer, the back-end write process will read the data from the data files. Also, this one will be responsible together with the checkpoint, okay, to force write all the dirty data from the data buffer back to the disk. The redo log also, which at first in the redo log buffer, will write, okay, to the redo log files in the disk using the log write thread to force all the data consistent transaction log, okay, written to the disk. CM. The coordinated nodes have three main functions. The first function is like a routine to receive the request from the client side. Once the request is received by the data nodes, this one will generate the execution plan. Here. Once the execution plan is generated, okay, the CM will distribute, okay, the SQL statement to the data nodes which need to be processed. It may involve multiple data nodes. Each of the data nodes will execute the statements and generate the result and send back to the CM. Finally, CM will do another task, which is gathering. Join all the results from the DM, okay, join together, union together, and then finally send back to the client side. So now, first, let's talking about deployment models. There are three different deployment models. Normally, we're talking about the primary standby or the distribute. Primary standby is quite similar to the failover traditional architectures. We have one primary node which is read and write. It is open for the data query and data modification languages to be processed. There could be one or even two standby nodes or even more standby nodes, okay, to handle, okay, the read-only process. Okay, remember here, there's a key difference. The standard standby architectures provided by the other environment like Oracle, okay, standby nodes by default is not readable. However, in Huawei GaussDB, okay, the standby nodes is read-only, which means if you have some of the reporting, okay, this kind of reporting actually can be running on the standby nodes. Okay, so that, okay, to release the load from the primary nodes. Distributed deployment instead, okay, we have multiple, okay, thread. Each of the thread actually will have, as what we said, okay, has a distribute, okay, data allocated in each of the thread. Okay, and all the thread is working together, okay, to process the data concurrently, parallelize, and generate result back to the customer. In each of the threads, it may still have one primary and several standby, okay, to provide high availability and the multi-copy of the data to ensure the data guarantee. There is something called single node deployments. However, since these single node deployments have no high availability, it's highly not recommended to be used in the production. Instead, in case if you want to save some cost, okay, you can use that for the development or the testing environments. So now let's look into a little bit more details. First of all, let's talking about primary and standby cluster. So this is the first scenario. Okay, we have a tree AZ. Each of the AZ actually means a physical data center. We have a tree AZ in one region, which is in one city. So that inside this city, okay, we distribute our GaussDB into different physical data center to provide high availability. So you will see that, okay, the active data nodes is running on the maybe on the first server. And also, okay, we have other three standby nodes across the AZ1 and the AZ2. The AZ3 is more for the current server. Okay, just in case if there are any network break between the AZ1 and the AZ2 to avoid the brain break situations. In these architectures, in case if, for example, if the server 2 or server 3 or server 4 die, no problem, the server 1 is still active. In case if a server 1 is failed, okay, the server 2 will take the control and serve the request from the client side automatically. It will automatically switch to active mode. If both server 1 and server 2 in AZ1 is totally failed, okay, either the server 3 or server 4 will be wake up and become active to receive the request. Again, this active sections is handled automatically. All this kind of the wake up process is handled by the current server, okay, in third AZ. What will happen if the third AZ and the first AZ is die at the same times? In this case, okay, we only have AZ2 left. In this case, to avoid the brain break situations, the AZ2 will be remain named standby. So it requires some manual operations to access the AZ2 to tell him, yes, I already verified both AZ1 and AZ3 is died. So I will manually wake up active the service in AZ2 to allow the access to be guaranteed. In this kind of the environments, in case if one of the server is died, the RPO is always 0 because there is a synchronized data replication between all the data nodes. There are 0 data lost, and for the RTO recovery time object, it's less than 10 seconds. This kind of automatically switch over will happen and finish within 10 seconds. This is a little bit complicated situations. So you will see that besides the first region, which is the first city, we may consider more safety mode to do the across region failover between the first region and the second region. Again, if just some server in the first region is died, you will see we have RPO equals 0 and RTO less than 60 seconds. However, in case if the total region 1, for example, one of the city, is totally have a network disaster or some natural disaster, totally fail. The region 2 can be wake up and rename the business. However, since the data replication between the region 1 and the region 2 is asynchronized, there might be some data lost. In most suitable situations, the RPO is less than 10 seconds. And the RTO, since in this case, we also need to manually bring up the service, it's less than 10 minutes. Now let's looking for the distributed cluster deployments. So you will see that in this kind of a case, for single region, both AZ1, AZ2, and AZ3 has some service running. Okay, so first of all, let's see, all the CM nodes, so the coordinate nodes is always up. Okay, all of them is active, receive the requirements, from local size and process accordingly. We have one primary cluster managers, one primary etcd, one primary GDM available. And for the data nodes, you will see that, for each of the ship, there will be one primary nodes, deployed in one size, and there will be one standby nodes deployed in each of the other AZ. In this kind of a case, you will see, even the AZ1 and AZ2, both of the AZ is dying. Actually, you will see that in AZ3, we still have the full set of data, which means there will be zero data loss. Again, for the distributed cluster deployments, we also support cross-region replications. So in case if the first region is totally died, we still can break up everything in second region and resume the business as usual. Now we finished the GaussDB architectures and the deployment models. So now let's go a little bit more details to looking into the SQL agents and storage agents. SQL agents. First of all, when we received the statements from the client side to the data nodes, it will go for the lexical analyze to identify all the keywords and then the token after the keywords. Keywords will be, for example, select. Because after the select will be something like a table name or select some column name. So also after the select, we identify the column name, as a token. This is the first step. The second step, we will do the syntax analyze. We need to understand, for example, after the select statement, there should be a from. All these kind of things will be analyzed, in the syntax analyze, and finally generate a path tree. After the path tree is generated, now we need to identify all the tokens. For example, if we select something from something, the from something should be a table. So we need to verify, looking into a database dictionary to verify, we do have this table exists to meet the SQL statement to be valid. All these kind of things will be done in the semantic analyze. Finally, we generate the query tree. Definitely, after we generate the query tree, there might be a possibility, to have multiple different query trees. In this case, for example, if we see that, we have a 4 table join, it could be join 2 first, then join the second one and the third one, like the one shown in the left. Or we can join AB, join CD together, then finally join the results again. Inside the database agents, how to define which one will be the best? We base on the cost of all the possibility, explain and decide which one has the least cost. In this case, for example, we calculate, for the first script pass, the cost is 1,000. However, in the second one, the cost is only 100. Definitely, the extreme plane of the in the right side, we are win. So how to optimize the extreme plane? First of all, we will collect the status. The status will be initial import of the cost optimization, which is driven from the basic table structure. Once we have all the table status, then we will estimate how many rows will be returned, for your queries based on all the cost estimations and optimizations. Then we will also calculate all the operators. For example, the join tables, the stack our tables and so on, okay, to calculate the final execution cost. Then based on all the execution queues, okay, we will find which one is have the best, okay, talking about the minimum, okay, cost to be selected. Then we will generate the execution plan based on that. What we're talking about is mainly, okay, for the primary and standby architectures. For the distributed architectures, it's a little bit more complicated. The reason is that, okay, we may involve the data query across different data nodes. In the primary standby nodes, all the active data is just in one node. However, if you want to see this kind of situations, we have an application, okay, try to get the data from the coordinate nodes submit to the GaussDB. The coordinates will receive the request and submit the requirements maybe to multiple data nodes. And in this case, okay, for example in here, the DM nodes 2, okay, try to do a table join. However, as what I said before, okay, the data is distributed, okay, to different data nodes. Some of the data required for the join statement in the data nodes may not exist in these nodes. In this case, it will involve another operators, okay, to retrieve the data from the data nodes 2, maybe to data nodes 4. There are several different kind of approach to be able, for example, broadcast, okay, gathering, and redistributions. Broadcast means the data nodes for realize that this kind of data may required by many data nodes, and it will broadcast the data nodes, that kind of that set of data to each of the data nodes. Redistributions actually is more common. It means I only, okay, distribute, okay, the data which is only required by the data nodes 2 and submit just to data nodes 2. Also, we have lots of the so-called the execution operators. So we have 4 major type of the operators. First thing, we're talking about the scan plane models. The scan plane models, okay, for example, typical models involve, okay, sequence scan, which is the full table scan, index scan, okay, scan by the index, or the subquery scan. All these kind of operations in memory done when you do a select statement from a tables. Also, we have some control plane mode. For example, okay, we have some kind of limit. Okay, limit is to say, for example, normally, okay, for example, when we try to select from a table, okay, maybe there will be 100 of the records to be appeared. However, if you only want to see, okay, 10 of the results, then you can say, okay, limit. Then only the first 10 rows will be retrieved. Also, the join is another, okay, control plane models. Also, we have a materialized plane models, okay. Some key example, for example, will be like aggregations and sort. Aggregation means, okay, group by or sum or average. Okay, sort is normally we're talking about order by. Also, we have a join plane models. Okay, we can do lots of table join, like a hash join, merge join, or the so on. So you will see here. Okay, so actually here you will see that, okay, in the bottom there are 2 full table scan, then join the result. Also here you have a see that there are 1 table full scan and 1 table, okay, retrieve the record by the index. And for these tables, okay, it will do a order by, then join this table with a merge join. The result will finally to be unit, okay, which is a control plane mode, okay, to retrieve and generate the final result and send back. A little bit, okay, more, say, explanations about the redistribution, okay, models in the distribute, okay, cloud instance. Why we have this kind of things? Actually, this is a very good example to display. Let's say we try to do a 2 table join. Okay, the join statement is a table 1.a equal table 2.a. The table 1 only have one column, okay, which is distributed key. So you will see that, okay, for the table 1, okay, since the distributed is A, okay, the 1, 3, 5, 7 is distributed to the first data nodes, okay, and 2, 4, 6, 8 is distributed to the second data nodes. Then we have the table 2. Table 2 have two columns, A and B. Okay, and the distributing key is A. So you will see that, okay, the data, okay, 1, 2, because the distributing key is A. So since the distributing key A equal to 1, so it's also distributed to the data nodes 1. Same, okay, the first, okay, rows, okay, A equal 3, A equal 5, and A equal 7. Okay, so these 4 rows is belong to data nodes 2, 1. Also, for the A equal 4, 2, 4, 6, and 8. Okay, since the distributing key A is are even numbers, so it's distributed to the data nodes 2. So now, first of all, let's talking about the simple example. So if we have an example, say A1.A equal table2.A, that's perfect. Okay, so because all the distribution key is the same, right? So for if we are doing the A1.A, table1.A equal table2.A, then the join statement is within data nodes. The data nodes of 1, okay, have everything meet this kind of criteria. However, in this case, it's different. It's table1.A equal table2.B. B is not distributing key. And you will see that, okay, for example, if you want to looking for the B equal 1, actually B equal 1 if it's here. So which means, okay, so this column need to be joined with this column, which definitely across two different data nodes. So how to do that? In order to do that, okay, first of all, okay, the distribute operators, okay, in the data nodes, okay, will inform the data nodes to, hi, I need to get some of your data from your data nodes. The data nodes 2, okay, we are using retributions, okay, to retrieve whatever the data is required and submit to the data nodes 1. Then the data nodes 1 will join the result, our table 1, and the operator from this one, which is the result of table 2, and join together to get the result. So this is why, okay, the across data nodes, okay, data retrieval and the distributions, okay, will be required in this case. These are very good examples for you to learn. Actually, in the real scenario, we should always recommend you to using the table 1 equal A, table 1.A equal table 2.A, which is avoid this kind of the cross data nodes queries. If you really have to do this kind of table 1.A equal table 2.B, then first of all, keep in mind, this one will take much longer time since lots of data will be go through different data nodes. Now, let's go for the storage agents. The storage agents, first of all, you will see it's after the SQL agents. Storage agents will receive, okay, the data query from the SQL agents, and it will go for the two different data table format. First of all, we are talking store for the appender and the uStore for the update pandas. So we will explain details in the later slides. Either one of them, okay, it will first of all looking for the data in the share buffer. If it's okay, then definitely the data will be directly go back to the client side. If it's not, okay, it will talk to the media managers to either get the data from the local disk or from the cloud-based storage services. Also, there is some extra internal process, okay, for example, especially okay, the log systems. Okay, this one will keep on record and write down all the transaction log, and also it will send the transaction log from the primary nodes to the standby nodes to make the data consistent. Some of the basic concept First of all, we have a database. So in each of the cluster, we may have multiple databases. Each of them, okay, is isolated. Inside each of the database, okay, you may have multiple schemas. Schema is a logic concept, just like a group of the objects. Then we have a table space. In GaussDB, the table space, the concept is not same as Oracle. In Oracle, table space is a logic concept. It contains multiple physical data files. In GaussDB, we are not. Okay, we don't have the data files concept. The table space itself is a physical files. Okay, so you can consider in GaussDB we combine the concept of the table space and the data files to make it both physical and logic. Finally, yes, okay, we have our tables. So how the things to be grown is that, okay, first of all, each of the tables will belong to one table space. And each of the table, okay, logically will belong to just one schema. But definitely, one schema can contain multiple tables, and one table space physically can store multiple tables. Index. I think index is a very common concept. So in the GaussDB, we have both single column index or the multi-column index. And then we have unique index, functional index, partition index, and full text index. Also, inside partition tables, if we require, we still can create a global secondary index. These architectures, tell us how the data file is or the table space, is stored inside the database. So you will see that inside each of the data nodes, there will be three important directories. Basic directory, which contain all the database IDs and all the reference file nodes. We have a Go directories, which will contain all the global system category informations. And we have this PG table space, which contain all the physical table space informations. You will see that, for example, if we will create a table space, so if we create the table space, using the definitive, direction name, it will do two things. The first thing is that, it will create this physical directory and store all the table informations. At the same time, it will also create a symboling in the PG underscore table space directories, which will point to the physical, directories, which locate all the files. So this is both steps, will be done. Create a physical files and create a symboling. Inside each of the table space, the table will be stored. So how the table stored? You will see that, inside each of the table space, then first of all, it will create a subdirectory for the database ID. Inside database ID, you will see the reference file nodes, which is the table reference ID. So each of the files, the size is 1 GB, which means if the total size of one table is less than 1 GB, you will only see one file. However, if the table increased to more than 1 GB, it will create the secondary file, which is the context, .1 or .2 until totally, it can go to maximally 22 TB, which means 32,000 tables, 32,000 files, for this table. Also, it will create a free space mapping files in here. Each of the plate will map, to MB blocks. Also, for this, we have data visibility files, which means each of the bit, will map to the MB files. All these two files will be used when we try to clean your database. So inside each of the files, it will be break into 8 pages. So you will see that, okay, they have multiple AKP pages. Inside each of the AKP pages, okay, there will be head, okay, and there will be a special character for the ending. There will be an item, which is a pointer, stop after the header. And also there will be a chunk, which actually are real data records, okay, to be stored, okay, in the bottom of the pages. The items which point, okay, will point to the real address of the data blocks. Otherwise I said, so first of all, okay, let's talking about in-place update table. Actually, this is like what I said you store. The key important things of you store is that, okay, you will see you have the undo tables, undo space. So this undo space, okay, will recall all the before images of your transactions. This kind of things, okay, will be used, okay, in the flashback operations, okay, when we try to quickly, okay, retrieve, okay, all your past transaction histories. Either the insert, update, and delete before the real data is updated in the block, okay, all the before image will be written into the undo table space. In another hand, for the A store, so you will see that there is no undo table space. Okay, if we want to do an insert, the data will be directly insert. If we want to do an update, okay, there will be a flag to map to tell the old, okay, data is deleted, and then it will write the new data here. But okay, the old data will not write to the undo table space. For the delete, same. Okay, we will map this portion as a deleted. Now let's go for the redo logs. Redo logs is a very important concept. Okay, we are talking about no false outcoming policy when we try to write certain data or update some records. Because normally when we are talking about the dirty data right back to disk, okay, it's always scratch the block, okay, and then use for the batch write instead. Which means if you try to write some data, okay, which you update some data or insert some new data, okay, those kind of data actually is always, okay, random and scattered, okay, into the disk. However, the redo log is always sequentially and continuously. So when we do the commit, if we want to wait for the data to be read into a disk, okay, this kind of a random and scattered data block write will be take a very long time. However, the redo log write, okay, which is continuously and sequentially log entries is very fast. So when we do the commit, okay, we are not force the data to be run to disk, however, but definitely we need to force, okay, the transaction log right into a disk. This one will much improve your overview performance when you try to commit your transactions. The redo log have certain of the functionalities. For example, if there is a database fault, so that we can use that to recover data because all the transaction, all the changes is recorded in the transaction log. Also, in the high availability architectures, okay, we can use the transaction log to synchronize data from primary to the standby. Also, during the backup and restore, we can use the transaction to the point of a time recover. So you will see that, okay, during for the primary and the standby, okay, in the common concept, okay, the primary nodes will keep up, replicate the redo log to the standby nodes to different AZs. The detailed transaction after the redo log flash to the disk. Okay, the thread, okay, will read the data from a disk and then pass it from the primary to the standby nodes. The standby node thread will receive the redo log, write to the disk, and replace all the transaction back to the standby database, okay, to make all the data synchronized. There's another replication possibility, which is normally we call them logic replications. In this kind of cases, okay, we're not using the GaussDB, okay, transaction log, okay, to replace. Instead, okay, we are using a logical DIS, data replication service, to replicate data between the source to the destinations. Although it's not as that reliable and easy to configure compared to GaussDB, they do have some advantage is that, okay, since the DIS is logical, so the target database architectures or the platforms may not be the same as the GaussDB. So if you, for example, if you want to, okay, replicate your data from the distribute, okay, GaussDB in your primary nodes, maybe to adjust the primary and the standby to the target, then you can use the DIS to do that. For the GaussDB, okay, we have a very important feature we call the GDM Lite, distribute, okay, transaction processing. Why we have this one? Because for the common open source database services, okay, like MySQL PG, okay, or even some older, okay, commercial database services, they are using the snapshot, okay, to snapshot all the informations, okay, just in case for the data consistency. However, since the snapshot will record down not only my transaction, but all the transaction which is running, assume that, okay, in a very high transaction periods, we may have thousands or even millions of concurrent transaction parallels running. Okay, if you try to do a snapshot, each of the 1 million snapshot need to record down all the 1 million template status. That will consume huge of the CPU memory disk and also the logs, which in some cases will make your database totally not accessible. In the GaussDB, we're using the CSM, okay, to replace the snapshot. So that we were smart, okay, to identify that, okay, for example, in this case, okay, you will see that, okay, in this period, okay, we identify that, okay, the commit, okay, sequence number of the transaction 1, transaction 3, transaction 5, transaction 7, and the transaction 8 actually is not across this line. So when in the GDM Lite situations, we are not, okay, we don't need to record down all the status of all the snapshot, okay, for this period. Instead, we only need to record 3 transactions, okay, which is very, very, okay, big reduce the load, okay, from the high concurrent transaction situations. Another important concept is checkpoint. So otherwise we said, okay, we are using the no force uncommit, which means, okay, it may have certain cases that, okay, after the database initialized, right? Okay, or if we never do the checkpoint, okay, actually all the transaction is a keep on the transaction leg, however, maybe or none of the real committed data is returned to the disk. If that kind of a case happens, in case if you have a system crash, you need to do recover. You need to replay all these kind of months of the dead transactions before you can restore. The restore time will take too much longer times. So we do recommend, okay, during the non-peak periods, okay, you must do this kind of checkpoint, okay, to force, okay, all the dirty data in the memories to write them back to disk, which means after that, okay, you are not, for example, if you do a checkpoint here, so actually all the full backup after that already have all the commit data, and once if you require any restore, okay, you only need to, okay, restore transaction for this shortened periods. Buffer pool. The buffer pool actually is have two things. So the first thing that it have an ID. Also, it have a data block. The data block, okay, is just the copy of the data block in a data file, which is the AK. Now let's go for the last chapter, operation and management. So first of all, we're talking about the online script, okay, which is a very important features. Not same as others, otherwise we said our GTM Lite features enable our GaussDB performance, okay, to be increased linearly, okay, up to more than 1,000 data nodes. And more important, no downtime during the scan out. So during the scale out, actually there will be two phases. The first phases, okay, the data, the nodes will be added to the cluster. After the data is not added to the cluster, okay, otherwise I said, okay, we need to, for those kind of the, hash, list, or region tables, okay, the data need to redistribute, portion of the data will need to be redistributed, okay, to these data nodes. During the phase one and the phase two, there are totally no downtime. But definitely, finally, okay, we need to exclusive lock the tables. Okay, we need to change the data, change the data definitions to tell the tables. Okay, yeah, pattern of the data already located to these new data nodes. And for the future query and insert, okay, you must do this. Again, there's no downtime, but there will be a 70 seconds of the exclusive table lock, which means during that period, there will be no, during this few seconds, there will be no data modification happening for this table. Backup and flashback. So for Huawei, okay, we are able to backup the GaussDB to either to the OBS or the NAS. For the public cloud and HCS environments, okay, all the data backup will go to the OBS. And for the lightweight models, okay, you need to provide the external, okay, NAS, okay, for the backup to be happening. After the data is backup, definitely you can restore. You can either restore to the same nodes, okay, to override some maybe mistaken deleted tables, or you can restore to a new nodes, okay, which will you, for example, if you want to create your database, okay, to a new environments. Flashback. Otherwise, I said, okay, flashback is quite similar to what they do. Okay, it's keep the before images. So, for example, after you delete, okay, your some of the records you want to see what kind of the data is deleted, then you can use these flashback features. Again, for the flashback, it's only available to the U store. It's not available to the S store because in the S store there is no undo table space available. For the server upgrade, so definitely we have a so-called the in-place upgrade. Okay, in this case, okay, we need to stop the database instance. Okay, then upgrade the binaries. There will be a downtime happening. However, for GaussDB, okay, we do have the in-service upgrade. Two scenarios. First scenario we call the hot patch upgrade. So this one is more applicable for like security patches or some function bug fix. Okay, there is a totally no service impact for the hot patch upgrades. And if we want to do a major version upgrade, since for example, if we want to enjoy some new functions, okay, then you can do the ruling upgrades, okay, to upgrade either by the same nodes or each of the AZ, okay, for example, you can upgrade AZ1 first, then AZ2, then AZ3. So you will see that, okay, there will be only 10 seconds, okay, during the primary data nodes or CM nodes switch over, okay, for your services. Another important feature for security is that we have so-called a full equipped database. Now let's first start talking about, okay, what is the common situations. In the common situations, okay, with the client, try to run SQL statements. The SQL statement will submit to a database server, and with it write to the disk. Okay, definitely we have a common encryptions to encrypt the data before it write to the disk. So this provide, okay, common safe, okay, situations, which means in case if your disk has been stolen, no worry, okay, the data already encrypted. However, if in case, okay, if you have a DBA maybe will resign very soon, okay, each can log into a database server and store your data from a database layer. Okay, so what to do if we try to avoid your DBA to query your data? The solution is a full encrypted database. Here, instead of the encryption in the server level, you do the encryption in your client level. Which means when we insert some records, those kind of value already be encrypted before it even sent to a database server. But definitely in this case, when they write to a disk, the data is already encrypted. In this case, since the encryption key is only kept in your client side but not in the server side, your DBA are not able to de-encrypt your data because he did not have the encryption key. However, use this feature carefully, because if you lost your key in your client side, that's it. There is no key kept in the server side. So you will be fully responsible for the encryption keys. If the key is gone, then all your data will be meaningless. Operation. We do have the basic operation features, like we can admin all the instance to do a backup and to do the instant management, parameter configurations, and version management. You can also using our OM to do all the DR features. For example, you can create a DR environment between two database cluster and so on. You can using the log security features, and also you can using the platform operation features. For example, you can do the agent upgrades, and monitor all the tasks. The very important thing features here, we are talking about intelligent operation and management centers. So you will see that, we have SQL diagnostic and tuning features available. We can identify what is the history slow queries and give you recommendations on how to solve this. Also, for example, we can give you some recommendation which kind of index should be created or deleted based on the SQL query in our system. We also can do the security related issues and normal database operation and management. For example, we can analyze your objects and we can kill the sections here. Also, you will see that actually we are keep on improving our intelligent operation and management centers. More and more new features will coming very soon. Also, you can using the operation and management centers to monitor all the informations, such as the node information about your CPU, about your network, and the storage resource utilizations. Also, you can monitor the instance information like transactions, IOs, and the SQL performance. Also, you can monitor all the alert. The alert could be an instance level alert or the system level alert, for example, some of the hardware failures. Also, all the alert can be sent to integrate into the third-party alert systems through the standard syslog or the simple network management protocol. Finally, we will introduce the workload diagnostic reports, WDR. It's quite similar to the Oracle ADR. So in this kind of things, first of all, we can monitor all the database level status, all the load informations, all the CPU informations, IO informations, and memory informations, and also the wait events. Some of the key information, for example, in the load profile, you will see there's the P80 and the P95. That is 80% of your transaction average processing times, or the 95% of your transaction informations. Also in the wait event, you will see all the wait which will most likely relate to how can you tune your database in case if you see any bottleneck. SQL statement status is very important in case if you happening find, for example, any CPU high CPU, high memory. Okay, then you can see from here, okay, all the SQL statements, okay, for what kind of the SQL statement, okay, consume most of the CPU, okay, most of the I/O rows retrieve. All this kind of information can be seen. Then from here, you can understand why this SQL statement have problems. For example, maybe they don't have the index, okay, to be created, so they are doing a full table scan for a very huge tables. All this kind of information can be seen from this WDR report. And that's all for this chapter. Thank you.